Hello everybody out in YouTube land. Welcome back to another exciting lesson in calculus. Last time we talked about this idea of implicit differentiation. And that idea is to be able to take a derivative of something that's not necessarily a function, because you might get two y values for the same x value, or in other words, two output values for one singular input value. And one example that we went through yesterday was this. Here we have a circle that's centered at -2, -3, and it has a radius of 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and so on. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Not exact, but so we get this circle here, right? It's not explicitly written as y equals. And so if I want the derivative at a singular point, I would have to give more information than just when x equals something. So if I wanted the derivative when x equals 3, well, I have two output values that I get for x equals 3. So technically, I would get two separate slopes depending on which y value I'm talking about, okay? But we talked about taking the derivative implicitly, treating x as a variable, and treating y as a function. So remember, the derivative of x is 1, where the derivative of y is just y prime, because we're taking the derivative in respect to x. Well, today we're going to expand on that idea and talk about taking second derivatives implicitly, okay? And that's exactly our goal, to be able to take a second derivative of an implicit equation, right? So with that said, let's go ahead and take a look. It's just a lot of practice today more than anything. Nothing new, just the combining of the idea of second derivatives with what we talked about the other day. And we did this problem actually on the last video, so we're going to skip that. If you want to go back over it, watch that video. But let's go ahead and look at this one. It says 2x cubed minus 3y squared equals 8. And we are looking for the second derivative there, right? And just in case some of you might be wondering, why is the second derivative written like this? How does this make sense? Well, remember that dy dx means the first derivative. It's the change in y over the change in x. Okay? We are not squaring this to get to the second derivative. If I put something like this, dy squared over dx squared, that is actually saying take the derivative and then square the result, which has no application or context to what we're talking about. So we're not taking the second derivative by raising it to the second power, even though you see exponents here like that. Rather, understand it this way. We're taking the derivative in respect to x of y, right? So that's what dy dx means. That's what y prime is. We're taking the derivative of y in respect to x, and if we multiply all this out, we'd see this is y over 1, so dy over dx. Now, if I'm taking the second derivative, what am I doing? I am taking the derivative of this guy, the derivative of this result. So the second derivative would look like this. It'd be d dx of d dx of y, okay? And then if we go to simplify this, we can see, if just thinking algebraically, we have d times d, in a sense, or d of y over dx dx. And so we write it like this because we can see d squared y over, and then all of this, technically you'd say dx squared, but then we just write it like that to represent this whole thing being squared. So that's where the notation comes from, just in case you were curious. But we are looking for the second derivative of this guy. Notice it's the second derivative of y in respect to x. So let's go ahead and find the first derivative. So the derivative of 2x cubed would be 6x squared. And then if you're going to treat it, or if you're going to think about it as a chain rule, which is always a good idea, if you think of this as chain rule where x is the inner function, then we would say, okay, the outer function, the derivative of the outer thing is 6x squared, and then times the derivative of the inner thing, well, the derivative of x is just 1, okay? The reason I think of that, I always want to think in terms of the chain rule so I don't miss anything. Because here on the negative 3y squared, we have to treat y as a function, right? We have to do the chain rule. So the derivative of this is going to be negative 6y to the first power, and then times the derivative of y, which is y prime. Now here's where notation gets really gross, because this is y to the first power, because remember we subtract 1 from the exponent, and this is prime, it's the derivative. So we have to be very careful with our notation here. So it might be better, instead of calling it y prime, that we call it dy dx, all right? And then the derivative of 8 is just 0. So there we have the derivative expression. Now we have a couple ways to go about finding the second derivative. We could isolate the first derivative and then take the second derivative, or we can just take the second derivative or take the derivatives of both sides again, and you'll see that we end up with a second derivative. I'll go ahead and do it both ways so you can see what it looks like. The first thing I'm going to do is, like method 1, I guess you would say, is take the derivative of this. Now, you got the 6x squared times 1. I'm just going to rewrite that as 6x squared, just to keep that simple. Now, taking the derivative of this, we end up with 12x. And then we have a sum and difference rule here, and we have a product rule here. So be careful with that. What's the derivative of the first thing? Well, we'll say the first thing is 6y, and the second thing is dy dx. What's the derivative of negative 6y? Well, that would be negative 6y prime, or negative 6 dy dx, right? And then times the second thing, so times dy dx, and then plus the derivative of the second thing, which we would write as d2y over dx squared, and then times the first thing, so times negative 6y, and I'll go ahead and put parentheses around everything there, plus there, just so we can see the product rule. Derivative of the first times the second, plus derivative of the second times the first, and then on the other side, again, the derivative of 0 is just 0. Now, well, this is what I just explained, is if I was to simplify this, is dy dx times dy dx, is that the second derivative? No, it's dy dx squared. So we would say 12x minus 6 times dy dx squared plus d2y over dx squared. Well, let me simplify that. Whoops. Let's say minus 6y times d2y dx squared equals 0. Now our goal is to be able to get the second derivative by itself, because it says what is d2y over dx squared? What is the second derivative? So we need to isolate this, and therefore we've got to move everything else over. So I'm going to subtract the 12x. I'm going to add this 6 dy dx squared. So we end up with negative 6y times d2y over dx squared equals 6 dy over dx squared minus 12x. And then we'll go ahead and divide by the negative 6y. So we end up with d2y over dx squared equals 6 times dy over dx squared minus 12x all over 6y, and then the negative 6y. And so that can reduce to d2y over dx squared equals, that would be a negative, if you want to write it that way, dy dx squared, and then plus 2x over y, okay? So we could write it like that. The problem is we don't want to write the second derivative in respect to x, y, and the first derivative. So what we need to do is get it down to at least where it's just x and y's. So we're going to have to replace this dy dx with what it's equivalent to, so that it's all in terms of x and y. So going back up here, we have an equation that has just the first derivative in it. If I'm going to go isolate dy dx there, I would get negative 6y times dy dx equals negative 6x squared. And then I'll divide by negative 6y, so I got dy dx equals, divide by negative 6, that becomes positive, so you end up with x squared over y. And then I can take that and plug it in right there. So we end up with negative x squared over y, all squared, plus 2x over y. And then that would simplify to negative x to the fourth over y squared plus 2x over y. And we don't want a fraction over a fraction, so we're going to rewrite that as negative x to the fourth over y cubed plus 2x over y. So this is my second derivative there. And that honestly looks clean, but the work here is really, really intense. So let's go ahead and look at it maybe a different way to see if there's a simpler way of seeing it. Okay? Now I'm going to use the Newton form here, and I'm going to isolate dy dx or y prime early, and that should make it a little bit easier. Let me rewrite the problem here. We have 2x cubed minus 3y squared equals 8. Again, taking the derivative of that, you end up with 6x squared minus 6y times y prime, keeping in mind that's a prime, equals 0. Then I'm going to go ahead and isolate y prime, so I got negative 6y times y prime equals negative 6x squared. And so we end up with y prime equals x squared over y. Okay, that's great. Now I want the second derivative. So I'm going to take the derivative of both sides. The derivative of y prime is y double prime. The derivative of this side is going to be the quotient rule. So the derivative of the top thing is 2x times the bottom thing, which is y, minus, well, what's the derivative of y? That'd be y prime times the top thing, so times x squared, all over the bottom squared. Okay? We can simplify this, I guess, a little bit. Well, we really can't simplify this other than get rid of the parentheses. But what I can do is replace the y prime with x squared over y. So I end up with 2xy minus x squared over y times x squared all over y squared. And then we can simplify that a little bit. So y double prime equals 2xy minus x to the fourth over y all over y squared. And then that can simplify to 2x over y minus x to the fourth over y cubed, which is exactly what we had in the last case. But you can see that this method is a lot more efficient, even if you want to call it dy dx here. If you isolate y prime early or dy dx early, so it's by itself, and then take the second derivative, that's just going to make it easier for you. Now, you might argue, well, why can't we just isolate y prime early, or sorry, isolate y early and take the derivative? Well, the problem with that is if I'm isolating y, I'm going to get y squared equals, divided by, we get negative, oh, there goes my lights, negative 8 over 3. Come on, lights, there we go. We get negative 8 over 3 plus 2x cubed over over 3. But then when I go to square root this, you have to keep in mind that y is then plus or minus radical negative 8/3 plus 2x cubed over 3. So then when I go to take the derivative of this, I'm actually going to get two results. I'm going to get the positive version and the negative version out. And so that's defeating the purpose and the efficiency of implicit differentiation. So instead, take the derivative and then isolate y prime, because after you do that, you can see that you're isolating y prime and not having to take the square root and cause more of a problem. Okay? So hopefully that made sense for you. Okay? Let's go ahead and check our work to make sure that it makes sense. And there it is, 2x over y minus x to the fourth over y cubed. So there is the example. Here is a practice problem that's going to look very similar to this. So you're going to want to pause the video, see what you can do with this, and then come back and compare to see if you know what you're doing. Okay. So for this problem, we've got y squared plus y equals 2x plus 1. And our goal is to figure out the second derivative of y in respect to x. So let's take the first derivative. Well, what's the derivative of y squared? Again, think chain rule. It's 2y times y prime. Plus, what's the derivative of y? Well, that's y prime. And then the derivative of 2x is 2, and the derivative of 1 is 0. So you can see here that we have y prime. Well, what could I do with that? I could go about just taking the second derivative now, but I could clean this up a little bit before I do. I could factor out a y prime here, so I end up with y prime times 2y plus 1 equals 2, and then solve for y prime, so you got 2 over 2y plus 1. So there is y prime. Now we want the second derivative, so we'd say y double prime equals, here we're going to have to use the quotient rule. The derivative of the top is 0 times the bottom minus the derivative of the bottom. Well, what's the derivative of 2y? Remember, 2 is a constant, so ignore it. What's the derivative of y? It's y prime. Bring the constant back in. So it would be 2y prime, and then times the top, which is 2, all over the bottom squared, so 2y plus 1 squared. So there's our second derivative. I'll clean that up a little bit. That all cancels out. So you're left with negative 4y prime over 2y plus 1 squared. Again, we do not want to leave it so that there's a y prime. We don't want the second derivative to be written in respect to y prime. We want it in respect to x or y or both, but not y prime. So we need to replace y prime with what we know it is. Now it's this. So we'd say negative 4 times 2 over 2y plus 1 all over 2y plus 1 squared. And then we can simplify that a little bit. We can say the second derivative, negative 4 times 2 is negative 8. And then all of this would go together to say 2y plus 1 cubed. And so that is our second derivative. And because it's written in Leibniz form, we'll just go ahead and replace Newton form with that. 2y plus 1 cubed. And so there is our second derivative of this function written implicitly. All right, let's see how good I am. A negative 8 over 2y plus 1 cubed. Hopefully you got that one right. All right, let's go ahead and take a look at another problem here, another practice problem that I'd like you to see if you can handle, and then come back and compare. Find the points on the curve x squared plus xy plus y squared equals 7. Find the points on the curve where the tangent line is parallel to the x-axis, where the tangent line is parallel to the x-axis. So a lot of times in our calculus problems, we have to think through this. We have to go, okay, what is it really asking for? I've got to translate this language into something that I can work with. Well, tangent line is parallel to the x-axis. Well, parallel lines have the same slope. And if it's parallel to the x-axis, well, what's the slope of the x-axis? The slope of the x-axis is 0. So we want a tangent line that has a slope of 0. Well, remember, the slope of the tangent line is the derivative. So we are looking for when the derivative is equal to 0. So let's go ahead and take the derivative. We would say the derivative of x squared is 2x plus, now we got to use the product rule here. The derivative of x is 1 times y plus the derivative of y, which is y prime, times x. And then chain rule, plus the derivative of y squared is 2y times y prime, and the derivative of 7 is 0. So there we have an equation, and we are looking for, let me go ahead and translate, therefore, when y prime equals 0. If it's parallel to the x-axis, that means the slope is 0, which means the derivative is equal to 0. So I could make this really easy. I don't have to even solve for y prime. The problem did not say find y prime. It said find this. As a result of that, I don't have to go through all the work to isolate y prime. I can just replace y prime with 0. So this is going to say 2x plus y, that simplifies to that, plus 0 times x plus 2y times 0 equals 0, because we want y prime to equal 0. And so this all cancels out, and we're left with 2x plus y equals 0. So anywhere where this equation holds true, you will find the tangent line is parallel to the x-axis. Well, we can go further. We can actually find the coordinates, because we have this equation that we know is true. Anywhere that this is true, we find our point on the graph. Well, here is the equation that we started with. So what I can do is I can treat this as a system of equations problem. And so I'm going to isolate y here, and I get y equals negative 2x. Then I can take that and substitute it into the y values here, so that the only variable is x, and I can solve for x. So that would say x squared plus x times negative 2x plus negative 2x squared equals 7. And so we end up with x squared minus 2x squared, and then this one's going to be plus 4x squared equals 7. So that's going to be what? Negative 1. That's going to be 3x squared equals 7. X squared equals 7 over 3. There is no domain restriction here, so when I square root this, I get x equals plus or minus radical 7 over 3, or x equals plus or minus rad 7 over rad 3. Okay? So now I found my x values for where this is true. Now I need to find my y values that correlate with this. So I'm going to take that, and I could either plug it into this guy for x to solve for y, or I could use this equation right here. This one's a lot simpler. So we would have y equals negative 2x. So negative 2, I'll do both of them separate. I'll do the positive version first. So negative 2 times rad 7 over rad 3. And we also have y equals negative 2 times negative rad 7. Oops. Negative rad 7 over rad 3. And so that becomes y equals negative 2 rad 7 over rad 3, and y equals 2 rad 7 over rad 3. And so the two coordinates are going to be rad 7 over rad 3, comma, negative 2 rad 7 over rad 3. And for this one, when we plugged in the negative, negative rad 7 over rad 3, comma, 2 rad 7 over rad 3. And that's our answer. Now we could rationalize the denominators there, so it would be rad 21 over 3 minus 2 rad 21 over 3, and so on, but we don't need to do that. Those are the two coordinates where whatever this graph looks like, has horizontal tangent lines or parallel lines to the x-axis. It's just another way of writing the same thing. Okay, let's go ahead and double check my work. I've got negative 2x minus y over x plus 2y. Oh, in this case, I did solve for y prime here. Okay, so here I factored out the y prime, I moved everything over, and then I isolated y prime. It would be a good study to make sure you know how to do that. In this case, I didn't need to do that, but it would be a good thing to make sure you know how to do, because if I just said what is y prime, or what is the second derivative. So we end up with that equation, y equals negative 2x. We plug that into the original one, and we end up with plus or minus rad 7 over 3, and then the y values as a result of that. And so we end up with the coordinates of rad 7 over 3, comma negative 2 times rad 7 over 3. That's just another way of writing it. Okay, so that is an example of using implicit differentiation in a non-function relationship. Okay. All right, I believe we have one more problem, and we will be done for this lesson. Let's see here. We've got x squared y equals 3y to the fourth what is y prime? So x squared y equals 3y to the fourth. What is y prime? So on this side, you should recognize that we have a product. And so we would say 2x times y plus the derivative of y, so plus y prime times x squared. So we did the product rule on the left. On the right, we have to use the chain rule because y we are treating as a function. So 3y to the fourth, that would be 12y cubed, and then times y prime, because the inner function here is y. So 12y cubed times y prime. Now we're looking for y prime, so we want to isolate it. What's the most efficient way? Well, probably to move this guy over here. So we end up with 2xy equals 12y cubed times y prime minus x squared y prime. I just subtracted that and flipped those over. And then we're going to go ahead and factor the y prime. So we have 2xy equals y prime times 12y cubed minus x squared. And then we'll divide all of that. So we got 2xy over 12y cubed minus x squared equals y prime. And that is our answer. Okay? So let's compare and see what happens here. Looks like we have the exact same thing. Now, another way to approach this, it looks like, let's see, what did I do here? You could have simplified that further. I guess what I'm getting at here is the idea, you might have recognized it earlier, that since both sides have a y, maybe I could just divide both sides by y. So I'd end up with x squared equals 3y cubed. And then, so if I took the derivative of this, I would end up with 2x equals 9y squared times y prime. And then isolating y prime, we end up with y prime equals 2x over 9y squared. And you go, well, that looks a lot simpler to me. And yeah, you're probably right. The question then becomes, are these really equivalent? Are these really equivalent? Well, looking at this relationship, when I divide both sides by y, I've got x squared equals 3y cubed. So this guy here can be replaced a little bit. This can turn into 2xy over, and I'm just going to solve for y cubed here. So y cubed would be y cubed equals 1/3 x squared. And so replacing y cubed, we get 12 times 1/3 x squared minus x squared. Okay? And then we end up with 2xy over 4x squared minus x squared. And so we end up with 2xy over, those are like terms, 3x squared. And you might be going, well, that's still not the same thing. You're right. We can reduce the x and the x there if we wanted to. So we could even say this to be 2y over 3x. That's nice. But how does that equate to that? Well, looking at what x squared is here, there's lots of different ways to approach this. We can replace this x squared with that x squared. So we end up with 2xy over 3 times 3y cubed. And then that would simplify to 2xy over 9y cubed. And then you can reduce the y's there, and we end up with 2x over 9y squared, which is exactly that. The point is, there's a whole lot of different ways to write a derivative when you're talking about implicitly, right? And none of them are necessarily wrong. It's just that you have to be careful that you're doing your algebra correct all along the way. If this was a free response question and it was saying find y prime, you'd be fine right here, okay? You would be fine there. You would be fine down here or here. All of these are equivalent to each other. Now, if it's a multiple choice type of question and you get to this as your answer, but none of the possible answers match this, that doesn't mean you're wrong. It just means that you have to manipulate your answer algebraically, correctly, to match one of the answers that are given. Okay? So Again, let me double check to make sure that's exactly what I got here. And in fact, we do have that, 2x over 9y squared. All right, that wraps up this lesson. Just an extra practice on implicit differentiation and throwing in the idea of being able to take a second derivative using implicit differentiation. Like always, if you have any questions, please comment below. Don't forget to like and subscribe, and I will talk to you next time.